So generally speaking, inverse functions are functions that undo each other. So I think about inverses as like my little twin sisters who whenever I would do something, they would undo it. Sorry, making Katie. So like for example, if my one function was x squared, the function that undoes it is root x, and the notation for inverse is a little exponent of -1. What would the opposite function or inverse function of 3x be? 1/3 x. You multiply a number by 3, you undo that by dividing that number by 3. And doing those repeated operations is an example of function composition. You do one thing and then do something else to the answer that you got. When I first give this example in like an Algebra 1 or Algebra 2 class, I begin with like a potato picture. And I say, here's my x's, and they're 1, 2, and 3. And they go to my y's that are 1, 4, and 9. Just make it an obvious pattern. So 1 goes to 1, 2 goes to 4, 3 goes to 9. That's the function f. The function f inverse takes that and reverses it. The x's are now 1, 4, and 9, and 1 is paired with 1, 4 is paired with 2, 9 is paired with 3, and that's the inverse. So if I take 2 to 4, you're like, aha, I'm going to undo you, I'll take 4 to 2. If I say 3 to 9, you're like, nah, I'm going to undo you, to take 3 to 9 back to 3. So in that case, the operation I chose was to square and then square root. But notice what happens with that. What happens to the domain of f? Where does it go in y? This domain's all the x's, right? The x's over here become the y's over there. What happens to the y's over here? They become the x's over there, right? In order to undo what someone's done, you've got to take their outputs and change them back what the inputs were, right? So this is a process of reversing things. And one technicality is that certain functions, one more picture, then I'll explain, we'll move on. If I say did -1 and 1, and I did the same operation I was doing, and I squared them, they're both going to go to what number? 1, does that make sense? And if you try to undo that, where do you send 1? Do you send 1 to -1, or do you send 1 to +1? How do you decide? And what's the problem with the second picture? Is that a function? Yeah, the second picture is not a function because functions are predictable. You put in an input, you get out one output. I told my high school kids they want them as machines. This is a machine that has 2 buttons that say Coke. You push this button and that button, they both give you Coke, right? Try to undo that. The question is, which button did it come from, button 1 or button 2? You don't know. It's like you push the Coke button and you get Sprite or Coke sometimes. You just don't know which. So that's one technicality we have to discuss about making sure certain functions can be functions. And the way you make x squared and root x be functions, you've got to only take certain x's, that's all. It's a technicality, but it's just something you should know. So a function is called 1, 2, 1 if it never takes on the same values twice. That is the... Yeah, quick.
So on that one, the one thing, so we can't do it.
Yep, that's a function that's not invertible. Yep, exactly, because the inverse that you get is not a function.
So if that was to come up, what would we say?
We'll get to it, okay? Just let me get there, because we'll get to it with actually equations as opposed to, you have to make a domain restriction. Just look at part of the picture. We'll do it with x squared. Okay, so a 1-to-1 function means that 1x goes to 1y. That's kind of where the word comes from. So 1x goes to 1y. In other words, the y's are not equal if x is not equal. That's what that second statement says. Your y's are different if your x's are different. So is that true for x squared? Are the y's different whenever the x's are different? In other words, you can think of an example where the x's are different, but the y is the same. 1 and negative 1, right? When you plug negative 1 and 1 into x squared, they both give you 1, right? So here is how you check if a function is 1 to 1. You use this thing called the horizontal line test. Have you heard of the vertical line test? Test that things are functions. So a function is 1 to 1 if and only if no horizontal line intersects its graph more than once. And here's why. So you've got some picture. We'll just say for specificity that it's like y equals x squared, okay? At x equals 1 and x equals negative 1, it gives the same y, right? So what this is saying is that 1 to 1-ness means every x goes to its own special y. Does every x here go to its own special y? No, these two x's have to share a y, and they're not happy because they want their own. That's kind of the idea. Would x cubed be a 1-to-1 function? Yeah, because x cubed looks like this approximately, right? Every x has its own special y, right? I don't think that's quite true, because I think that no, that's definitely not true. Sine is an odd function, right? Is sine 1 to 1? No, it's not. It's a good conjecture, but the answer is no. Yep. Has to do with the fact, does the function wrap back on itself? That's what it really matters. So the way to tell is just check and see, does a function wrap back on itself? So x cubed, is that going to be 1 to 1? Yes. Every x has its own special unique y. There's no sharing. And you can think about that because x cubed looks like this. Is x squared 1 to 1? No. Some x's have to, like 0 only goes to one number, but negative 1 and 1 both go to the same y, so that's not a 1-to-1 function. How about e to the x? It in general looks like this, right? That one is, yeah. And the reason is even though that line seems to kind of like horizontal and level out, it does keep slowly creeping down. Yeah?
Isn't there an e cubed function where it like curves like even more exaggerated, so it wouldn't pass the horizontal line?
Oh, yes, yes, yes. So there are examples of like cubic functions, so like maybe even x cubed minus x, for example. And that would do something like this kind of thing, where then it wouldn't be 1-to-1 anymore at all. But x cubed itself does not double back on itself at all. Okay. So mostly you should be able to figure out just by, it's like a basic function you know the picture of. Does that make sense? Or something where you're given a picture and you're asked, is this function 1-to-1 or not? Oh, if it fails the vertical line test, it isn't a function. So it loses its function. Yeah, it's not a function. And functioning means that every x goes to its. It has a predictable y. They can go to the same y, right? It's okay if two x's go to the same y, but it's not okay if x goes two places. Okay. So here is the definition of an inverse. So what this says, you have a function f who has domain A and range B. And the inverse function, we discussed how the fact that inverses flip-flop, right? So f inverse's domain is B and its range is A. And it's defined as f inverse of y is x if and only if f of x is y. Now, let's see if I can make that make more sense. Let's use the specific examples of x cubed and the cube root of x, okay? So you know that the cube root of 8 equals what? 2. And that's true because 2 cubed equals 8. So here, the cube root is like the f inverse, okay? And the cubed is the f. Does that make sense? Notice what happened. You put y in and got x out. So this is the y and this is the x. this thing is just flip-flopped. And really what you can think is that this question, f inverse of y equals x, what this is asking, when does f of x equal y? That's the question it's asking you to answer. Kind of like when you're first asked to find cube root of 8, you say, okay, what number to the third power gives me 8? And that's the question you ask yourself to get that it's 2. So let's do a couple things with actual numbers, because I must say variables also like make me kind of go a little bit like a Okay. One last thing about inverses is that they cancel each other out before we move on. So we had from the previous slide, just get my notes so you can see it. We had f inverse of y equaled x, right? And f of x equaled y. So these two equations come from taking these two things and doing replacement. So the first one, if I have f of x, using these things, what is x equal to? What is x equal there? F inverse of y, so that's f inverse of y. And inverses undo each other. We said, okay, well that thing was just equal to y. This is how you say formally that inverses undo each other. When you compose them, you get back to where you've begun. It's a fancy way of saying something like, if I take a number and I cube root it, and then I cube it, what do you get back? I'll say that's 8, because 8's easy. If you cube root 8 and then cube 8, what do you get out? 8. And if you do 8 cubed and then take the cube root, what comes out? 8. So doing one thing and then the other is an example of composition. Okay, so let's do some specifics here. So I told you f of 1 is 5, f of 3 is 7, and f of 8 is negative 10. Find the following. So f inverse of 7. The question you're asking yourself, just say that's equal to some x you don't know, is when does f of x equal 7? At which x does that occur? 3. So that means f inverse of 7 is equal to 3. Do you see how all that happened there is that what was inside was outside and they just flip-flopped? So,
I would only know that because you stated that.
Yep, if I haven't given you that point, you wouldn't know it.
Okay.
So we will definitely, we'll do these where we have a specific function. You can use the information about the original to get information about the inverse. But for these, yeah, you had to have specific values that were given. You couldn't have figured that out if I hadn't told you f of 3 was 7. Nope. So what's f inverse of 5 going to be? 1. And what's f inverse of negative 10 going to be? 8. And some questions like this might come up and you can, it might be, if I gave you f inverse of 10, you'd have to say IDK for real, not IDK like I don't know, as in like there's not enough information, right? So, because there wasn't information given about when this thing is equal to 10. Okay, and you can't assume it's negative a, you just don't know. All right, does anybody remember, did you ever have to find inverses before? Okay, how did you do that? Switch the x and y or something, yep. So this really is y equals x cubed minus 5. Switch it around to x equals y cubed minus 5. Doing this forces you to undo the operations in the correct order. So what do you do first? And so cube root it, and that cube root power doesn't distribute. And the proper notation is f with this little negative 1. You guys are in calculus now, so you should know that. Oh, I changed your equation? I'm so sorry. Wait, what did I change it to?
X plus 2 cubed minus 5.
Okay. So sorry. So y equals x plus 2 cubed. Well, the first step is still the same, right? X equals y plus 2 cubed minus 5. First step is still to add 5, right? Sorry, I was looking at my old notes. I guess I just didn't edit this. My bad. Next step is still the same, which is cube root it. You are totally allowed to interrupt me and stop me right away if that happens again, okay? Because I edited those papers, and these documents are different, so I have to go back and catch where I've made the changes, and it's not going to be perfect. Okay, what's the last thing you do? Subtract 2. So your inverse function is the cube root x plus 5 minus 2. You can kind of think that here's my explanation of this. So if you reduce up in the original, first you take x, operation 1 is add 2, right? What's the next thing you do once you've added 2 in the original? Cube it, and then you take away 5, right? If you're going to undo those things, you have to go in the opposite order, okay? So the last thing you did was took away 5. The first thing you do is add 5. That's why this comes first. Then you cube root, because that's the other thing you did in the middle, right? And then you take away 2. Mathematicians call this the shoes and socks principle. You put your socks on first and then your shoes. And to undo it, you do shoes first and then socks, right? It's the inverse. Back to bare feet. You don't want me to take my socks off and be smelly. So, okay. Sometimes solves cleverness. I mean, my pre-calculus kids do like a gazillion of these. They better remember. So find the inverse of this guy. So x equals 2y plus 3 over y minus 5. And the problem is now you've got to solve for y, and you've got 2 y's, and that's stupid. Yes?
It also asks
Let's do that on this one. The other one's easy, okay? Thank you, though. So what's the first thing you would think of doing on this question? Multiply by y minus 5. X times y minus 5 equals 2y plus 3, or xy minus 5x equals 2y plus 3. Okay, and, okay, so you can't I mean, you could divide by y, but that's really going to put y's in denominators, and that's going to be kind of silly, right? Any other ideas? Yeah, I'm going to move this y to the left side, and then move 5x to the right, although it doesn't matter which side you pick. The point is get all the y's on one side, everything that has no y goes on the other side. So xy minus 2y equals 5x plus 3. Is everyone okay with that? And take out a greatest common factor of y. That's how you make 1 into 2 into 1. And y is equal to 5x plus 3 over x minus 2. So f inverse is 5x plus 3 over x minus 2. And that trick where you get all of the things on the same side that have what you want to solve for will come up again in this class in section 3.5. It's just a different context. So the domain here, what's the one thing x cannot equal? 2. And you can tell that from the equation, right? So minus infinity to 2, union 2 to infinity. Now, ranges are harder to get from the equation itself because you're asking yourself, what are the possible y's? You could graph it, or you could use the fact that this is an inverse of a function you know. Does that make sense? So because this is an inverse of f, the range here is equal to the domain of f. And can you find the domain of f easily? Yeah, so what's the thing that x cannot equal for f? 5. So for the range, the y will not equal 5, because that flip-flopped. And you can give that as an interval as -infinity to 5, union 5 to infinity. And that's how I test that you understand that relationship, that to find the range, you've got to look at the domain of the original. Yes?
I know we normally have to put it in interval notation, but
It didn't say, and so since it didn't say, if you want to say the not equal to, the one thing I'll be picky about is you must specify that domain is x and range is y. Does that make sense? Like if you say x equals for both, that's actually incorrect. So if I don't specify and I don't say interval, make sure you specify that domain is the x, range is the y. That's the one thing you might get zinged on if you didn't do it if you did it that way. But yes, you can lawyer me if I didn't say no interval necessary. Okay.
You always have to put the interval in the notation?
Well, like Natalie said, if I didn't specify, I'm not going to be picky about it. So I'll either specify or you can do either.
I mean, it doesn't have a point to write that. As long as you say x then never equals 2.
You know, I don't really know. I think that the only reason I do it is to make sure you understand both notations in case you see them both. Does that make sense? But I don't know if there's any really specific benefit to one or the other than the fact that they're both used, so it's good to know that they're sort of synonymous.
I mean, because x does not equal 2 is equal to that.
Exactly, yeah. So unless I specify, it doesn't matter. Yeah.
Could you just find the horizontal asymptote?
It's the same thing. Yep. Mm-hmm. If you know how to find horizontal asymptotes, the value that y cannot equal is the horizontal asymptote. So yes, that is the relationship as well. Most people don't catch that though. So you could effectively trick me. Okay. Oh man. Okay, sketch the graph of this and its inverse. So first of all, sketching the graph of that function. Holy patoli. So there's negatives inside there. I'm going to write that as negative parenthesis x plus 2. Does that make sense? That's true at all? Okay. So this takes the function root x. What does it do to it? Flips it over what? Over the x, and then moves it
To the left.
Mm-hmm. And one way you can tell that that's the case is this will equal 0 when x equals -2. Does that make sense? Just like by plugging in some numbers and stuff. So it takes this root function, which looks like this, flips it, boop, boop, boop. Oh, just that one, and then that one, like this, and moves it over to the left 2.
We had said it would flip over the x.
I thought it was flipped over the x-axis.
I said over x, but I meant over y, because it definitely is over the y-axis. That's my bad. Do you agree that it's over the y, though? Because it's inside, yeah. Okay. Alrighty, so there is the picture of -2 minus x. Now, let's take that equation and do the thing where we solve for the y. So let's say take that and make it x equals square root -2 minus y. What's the first thing you do to undo the square root? Square it. And then you'd add 2, right? by -1. So negative x squared minus 2. Okay. There is a technicality here.
You just pull that x out at the beginning just to look at it.
Yeah, actually, it's a bit of a tricky thing, but you have to pull the negative out to get the transformation correct. So when there's a negative inside in front of the x. So that is definitely a bit tricky. Okay, so what does the negative x squared minus 2 look? It's a parabola, right? Shifted How?
Right, two.
Down 2 when it's first flipped over the which axis? Over the x. So it's going to be down here and look like that. I'll draw the whole parabola in now, and then tell me where there's a problem. So why is there a problem with this whole parabola? Is the whole parabola a 1-to-1 function? No. So you've got to figure out, look at your original. What was the domain of the original? Great. And what was the range of the original? What's the lowest y? 0. Does that make sense? Even though it occurs last, you still list it first, right? So what happens with the inverse? That flip-flops, right? Now, the domain of your inverse is what? And the range of your inverse should be minus infinity to negative 2. So if your domain is just 0 to infinity, what part do you keep? The part on the left of the y or part on the right of the y? Which part of this parabola is x is ranging from 0 to infinity? This half or that half? The right half is, right? So that's how you actually define inverses.
Why is the domain 0?
Why is, because this is the inverse of that root function.
Oh, so it has to.
It has to be. Yep. So my eraser went away, so I'm forced to use white marker. This part is not included.
Makes more sense.
Yep.
Because that picture you had.
Exactly. And notice that there's also a relationship between the graph of the function f and the graph of its inverse. It's reflection over the diagonal. And so one more thing, I'm going to ask you a question, okay? You have to, if this happens where you have to leave part of a picture out, you have to specify that that happens by saying x bigger than or equal to 0, at least in this case. That's what it is. Do you see what I mean by that? Because technically this parabola as an equation includes both sides unless you specify that you meant only part of it.
That's like just a statement.
It's an additional statement saying this parabola but just this piece. Yes?
For the original equation, you took out the negative.
Mhm.
So why wouldn't we take out the negative for the inverse?
Oh, you could do that here too. You could say negative parenthesis x squared plus 2. That's also fine. You just don't have to. The reason I did it in the first one was to get the graph, you have to have a negative expression of stuff to get the shift correct.
You didn't end up with
Let me come back to it, okay, because I've got too much other stuff to cover, but that is the technical reason. The point of this example was not that. It was really more that if you have something when the picture you get is not 1-to-1, you've got to tell me you mean only part of it. That's the part that's really important there. Okay. Okay, so this is where those logarithms come in. So technically, as long as your base isn't 1 and you've got that flat line function, your exponential function is 1-to-1 and it has an inverse. So for example, the function 2 to the x goes through the point 0, 1, 1, 2, 2, 4. That's the picture of f of x equals 2 to the x. It's a 1-to-1 function. It has an inverse. Its inverse is this function, log base 2. That is its name. And the way you construct points on it is you just take the points here and you flip-flop them. This point was 0, 1. When you flip-flop it, it becomes 1, 0, which is that right there, right? So there's 1, 0. This point was 1, 2. It becomes 2, 1. That next point was 2, 4 becomes 4, 2. What happens to the asymptote? So it was the x-axis, now it's going to be the y-axis. So there's a picture of f inverse of x is log base 2x. I think we did that with E and ln yesterday, right? Okay. If it was 3 to the x, you'd graph 3 to the x and then flip-flop those points to get log base 3, right? So the opposite of log base 5, 5 to the x. Opposite of 10, yes?
So is it always like the inverse is reflected over the y?
Yeah, it is always the case that the diagonal y equals x, that the inverse's picture is a reflection over that diagonal. That is always true. Yep. You guys see what she means? Okay. What is the domain of this log base 2 thing? And what's its range? All real numbers. Yep. Remember how I said yesterday that there are 3 commandments in this class and the third one is thou shalt not log negatives? Does that ring a bell? I think I said that right. And this is the reason. Because its domain or its inputs are 0 to infinity, you can't take a log of negatives. It's not possible. And we'll have some specific examples that also discuss it in more concrete terms, but that's the reason. Not a possible input. Your calculator is going to say domain error and it's going to cry and give up. And there's no corresponding like imaginary log numbers. It just doesn't, just don't do them. Okay, so because these functions are inverses, when you put them together, what are you going to get? So if I do g of x and then apply f to it, I get back what I had to begin with, which was x. Okay, so that's going to equal x. The question is what is that going to look like? So what's g of x equal to in this particular case? Log base b. And so f of log base b means you put that log base b into this picture, into that function, which puts the log into the exponent, right? So b to the log base b of x equals x, as long as those bases match. So if I had 2 to the log base 2 of, say, I don't know, 7, what's that going to equal? 7. Okay, now the technical restriction now is if you're going to do this, stuff has to work in log base b. So because that's true, you have to have x's bigger than 0. And you can't do negatives because you can't put negatives into logs. Terror will be smote upon you. This one, if you do the composition in the opposite order with inverses, you also still get x. It doesn't matter in which thing stuff is undone, it's still undone. So this becomes g of b to the x. And if you put that b to the x inside the log, you get log base b of b to the x. So if I wrote, for example, log 2 of 2 to the 7th, what's that got to equal? 7. And is there any funniness here? Like, is there any number you can't plug into an exponential? No, so in that case, it's for all x, as in, like, all real numbers are okay in that direction. Alrighty, great. Okay, so find the exact values of these couple logs. So revert back to the whole cube root analogy. How do you analyze like cube root of, we'll say 1,000 this time? What's the question you ask yourself in your head? Say what to the 3 equals 1,000, right? This thing, say equals what? You're asking, when you do roots, you're looking for the base, right? When you do logs, you're looking for the exponent. You're saying 5 to the what power gives me 125. Do you see what's kind of analogous to that? It's quite analogous to a cube root, right? Okay. And so, and as you can see that this 5 is the base there, it's the base there as well, right? So I think that happens for a nice number, doesn't it? I think it's 3. Yep. So that is 3. Okay, 2 to the what power makes 1/32nd? So what kind of powers make fractions like that? Negative numbers. So just think 2 to the what makes 32? 5, right? So this will be, but it'd be -5 because of the fact that you've got a fraction. Okay. And this is 9 to the what power gives you 3? Half. And that's because root 9 is 3, and root 9 is the same as 9 to the 1/2 power, right? Okay. Let's add just one more in. Let's try to do log base 2 of -4, just to illustrate why you really can't do these. So what's the question you ask yourself? 2 to the what equals -4, yep. And no matter what number you put into that, you get a positive result. Does that make sense? Like 2 to the positive numbers make positive numbers, right? 2 to the 0 is 1. When you plug in negatives, you get things that get close to but never get all the way to 0, right? So is there any number that you know of that'll make that happen? No. That's why that's another reason why it's not possible to do logs of negatives.
Is there any mathematical situation in which you would include imaginary numbers for the logarithm?
I mean, there might be, but I don't know about it. So you won't see it probably. If I haven't seen it, you won't see it. Unless you become better mathematicians than I am, which is totally possible. But not in your near future. Okay, and logs have weird properties, like these. Like, does it seem a little strange that when you log a product, you then can add the logs? Does that seem a bit weird? I think it's a little weird, maybe? So they come from a little bit from the rules for exponents. So I'm going to prove to you why one of them works, okay? And then we'll just kind of accept the others. So log base b of xy is the same thing as log base b to the log b of x b. Okay, for now, I would never ask you to come up with that trick on your own, but do you agree that that's actually true? Is it true that x equals b to the log base bx? Do you buy that? And you because of the whole cancellation thing, right? And you buy that b to the log base b of y is equal to y, right? I just did a clever thing. I watch a lot of Doctor Who, so British comes up all the time. Okay, and so then you're like, well, I know that if I have common bases and they're multiplied, the exponents do what? They add. So that becomes log base b to the one singular power of log bx plus log by. Okay? And if you have log b and then b to the stuff, what happens to this log b and this b? They cancel and you just get stuff. And so this is log bx plus log by. They come from the rules for exponents.
Does it cancel or become 1?
They, these cancel and just give you back the thing. Like when I had that being a 7, you would just get 7. And if this were like, x squared plus 2, you just get x squared plus 2. So this cancels and this cancels and just gives you that as a, normal size, no longer exponent thing. Let me just, one more thing, multiply. It's the same as the rules for exponents, right? When you multiply, exponents add. When you multiply, the logs add, right? Number 2 is almost the exact same thing, except for I put a division bar here, and that division bar would make this into subtraction. So that's the same thing. This next one is the thing about the power pulling down, and that one's actually pretty easy to explain with a specific number. Like if I gave you log base b of x cubed, That's the same thing as log b of x times x times x, right? And if you accept rule number 1, that means you have log b of x added how many times? You got log bx plus log bx plus log base b of x. How many log base b of x's is that? 3. So that's 3 things you're going to have to know. And I'm sorry it was so quick. Because I have like, oh my god, this is ridiculous. Class is not long enough. You guys are like, oh my god, yes it is. Okay. Okay, use properties of logs to express the following things as one logarithm. So log base 2 of 80 minus log base 2 of 5. So if you put these back together, they condense down to 1 log, and what happens to the 80 and the 5? They divide. What is 80 over 5? Oh, look at that was clever. What's log base 2 of 16? 4. So this one, what are those numbers in front actually? What'd they come from? They came from powers, yep. So that's log base b plus log of c squared minus log of d cubed. And if you put them together into 1 log, yeah, which things are b squared, c squared? B c squared divided by d cubed. Everything that is positive came from a numerator. Everything that's negative came from a denominator because you did something minus something else. You could also think that this negative could also be part of a power. It could be d to the negative 3rd power, which ends up in the denominator as well. Okay. Natural logarithms. So if you have e to the x, its opposite inverse is log base ex, which is usually written as ln. They just gave that one a special couple letters. I don't know why, they just did it. Not nice. Okay. So we're going to use that idea to solve some equations. So if you're solving this, what's the first thing you do? Add 1, right? So you have ln of x plus 5 equals 8. You've got to think, what is the opposite of ln? E. And what you've got to do is you've got to exponentiate both sides, which means that both the left side and the right side go into a power. And that's because then e and ln will cancel because they're inverses. So x plus 5 is e to the 8th, whatever weird number that is. And so x equals e to the 8th minus 5. What do you think the most common mistake students made when they did this with me in the past is? Any ideas? Here, instead of saying e to the 8th, they'd say 8e. Is 8e different than e to the 8th? Oh, heck yeah, it's hugely different. And that's the thing you've got to remember is that for these to cancel, it has to be inside of the exponent. Just make it obvious you put it into an exponent. And then if you calculator, maybe, if not, whatever, you know. Okay, this one. First step, -4. Now what do you apply to undo e? So 2x minus 5 equals ln 6. And that's just some weird number, so you've got to like ln it for anything else, but you know, just leave it alone. And now how would you continue getting x alone? Add. And can that 5 and that 6 can't combine? Nope, because 6 must be ln before 5 is added. On quizzes, you'll be asked to give exact answers, not approximations. Okay, and then this one we already kind of solved. We did something quite similar. So what would be the first thing you would do? Subtract 1. And then, oh, yep, sorry, thanks. Woo. Okay, and flip the sign, of course. I can't believe I missed that. Don't tell my Algebra 1 students I made that mistake. I'll be so embarrassed. Okay, and then what do you do to undo ln? E. So e to the ln x is less than, is e to the negative first an okay thing to do? Yep, okay. So you get x is bigger than e to the negative first, which is the same thing as 1 over e, right? So that will be 1 over e to infinity. All right. And then we have some pictures, and I think we'll have to do inverse trig functions tomorrow. So ln of x, sketch a graph of that function. We did this yesterday. So first you could sketch e to the x, which looks like that, right? That one has a horizontal asymptote. What will ln of x have? A vertical asymptote. And I don't care about like super specific points. I mean, I care that you know that it goes through 1, 0, and that you get the asymptote in the right place, you get the general shape correct, but just like that you get that ln looks like that. If you don't know it, flashcard it. So. And then you're asked to do some shifts, I assume, right? Like this. So take that ln of x picture, which you had graphed in the previous part, and shift it, left or right? And up 3. It now has a vertical asymptote at x equals 2 instead of x equals 0.